The second part of these problems is going to be looking at modeling given 3 points. So if we have a quadratic function, as long as we know 3 points, so in this case, they're showing that you have the roots and you have the vertex. So remember, if we say the roots are at 0 and 10, that is the two x-intercepts, so 0, 0, and 10, 0. And then if they give us the vertex 5, 8, then we now have 3 points that we can use, 2 and 3 as values of x and y, okay? So if we use the standard form of the quadratic equation, if I know the values of y and x, then that means the only things that I don't know are a, b, and c. Now, if I have 3 unknowns, I can create a system with 3 equations, and then we're able to solve for those 3 unknowns. So we're going to use each of those ordered pairs. So this one they used 0, 0. This one they used 10, 0. And this one they used 5, 8. Each of those ordered pairs plugged into the standard form equation. And when you simplify that down, we end up with this system. Okay, and so by using elimination and substitution, which we'll walk through together, this is all stuff that we did back in chapter 5. By doing that, we can solve for the values of a, b, and c, and that allows us to come up with this equation here. So that's going to be the extra little piece that we're adding into this last set of problems that we look at. So let's look at example 3. It says a bottle rocket is launched into the air from the ground at an initial upward velocity of 80 feet per second. The rocket landed 50 feet from the launch site. How long was the bottle rocket in the air? Okay, so we're trying to solve for time, and you'll notice the information they gave us is all about its upward velocity. So that tells me that I am interested in the equations involving y, because we're talking about upward velocity, so that's vertical. So I'm going to choose to use the equation y equals 1/2 g times t squared plus vy initial times t plus v initial. Or sorry, not v initial, y initial, the initial height. Copied that wrong. That's the equation that we are going to use, and they gave us lots of these pieces, okay? So let's work on this side first. We'll come back to y in just a second. So we have 1/2. This is talking about feet, so we need to use negative 32.2 for the acceleration due to gravity. Time we don't know, so that's t squared. Now, the initial vertical velocity they gave us up here, an initial upward velocity of 80 feet per second. So that's what we're going to put in there, 80y, plus y initial, and we're still working under the assumption that they told us on the previous problems that x initial and y initial are always going to be 0 for this project. So we're going to stick with that. Now, in order to solve for t, we have to decide what to make this equation equal to. And so the question is, what height do we want? So if we're trying to figure out the total time that it was in the air, we need to think about what this graph looks like. We're starting at an initial height of 0. We're going to launch the rocket, and as time goes on, it's going to go up, and then it's going to come back down. So we are curious about when it hits the second height. And at this point, the height again is 0. So that's what we are trying to solve for. We're trying to say, if we take all of these factors over here into account, when is our height going to again be 0? Okay. So when we set this up, we get negative 16.1 t squared plus 80. That should be a t, not a y. I don't know what I've got going on here. That's a t. So 80t. Now, I would solve this one by factoring. And when we've got decimals, it's okay. It's not going to factor out necessarily evenly. I'm going to factor out negative 16.1 t. So that gives me t minus, I'm going to get a decimal over here. What is that decimal going to be? Just one moment. We are going to get minus 4.97. So if we set each of these equal to 0, here t is going to be 0. We knew that because we started at a height of 0. And then here t is going to be 4.97. So that's the one that we're going to work with. The total time that it was in the air was 4.97 seconds. Okay. So the next question is, what was the maximum height of the bottle rocket? Well, now let's go back to our picture, because we know a little bit more now. We know that this is at 4.97. So once again, where does the maximum height happen? That's going to be half of this time. So we need to figure out what time we want to use. So we want half of 4.97. And that comes out to 3 decimals. And I'm going to keep all 3 of them, 2.485. That is what we get when we divide that out, okay? So we are trying to solve for y again this time. Now we want to know the height, which is y. So y is going to be equal to 1/2 times our old friend gravity again, negative 32.2, times t squared, and we're going to use 2.485 for t, because that's the time we're interested in, plus 80 times 2.485. And then again, that plus 0 at the end really doesn't matter, but that's part of the equation. When you crunch all of that down, you get a answer of 99.37, and that is the maximum height in feet. So that's not too bad. Always remember that the vertex is going to be halfway. It's always halfway between the x-intercepts. Okay, the last one is a little bit more labor intensive, but as systems go, it could certainly be worse. So it says, write an equation that models the path of the bottle rocket with respect to distance and height, using what we looked at in that previous example. And so here's what we know. And this is where that last bit of information, you notice we haven't used the fact that they said it traveled a total distance of 50 feet. That is important because that's one of the points that we have to use. So we know 3 points, 0, 0, 50, 0, because it goes a total distance of 50. And then halfway there is going to be 25, and we just figured out that the height was 99.37. Now, one thing that I want you to notice is now we're changing the variables. We are trying to write an equation that contains both x and y, distance and height. So the part B, we were looking at height versus time. So that's why we're not using time here anymore for x. And that's why you remember the t value that we got in part A was a little less than 4 point something, something, something. And that was our x-intercept, 4.97 maybe, 98. I don't remember. I can't see it on my screen anymore. That's what we were looking at there. But now we are wanting an equation that's height versus distance. So now this point over here is going to be 50 feet. We're no longer talking about time. Time's not going to be a part of this equation that we're writing, which is why we can't use those kinematic equations anymore and why we have to do this extra work with the system. So those are the 3 points now that we have got, both in terms of x and y. So when we have a horizontal distance of 0, we have a height of 0. A horizontal distance of 50 feet has a height of 0 feet. And when we are at a horizontal distance of 25, we are at a height of 99.37. So it's kind of interesting how we're changing back and forth. And this is why it's so important that you keep track of what your variables are. All right, so we need to substitute that into 3 different equations using the standard form y equals ax squared plus bx plus c. We are going to substitute in our x's and y's into this 3 separate times. Okay, so when we are at 0, 0, the equation is going to be 0 equals a times 0 squared plus b times 0 plus c. And if we simplify that down, we are going to get that 0 equals c, because those zeros are going to cancel everything out. Okay, next equation is at 50, 0. So again, y is 0 in this case, and we get a times 50 squared plus b times 50 plus c. And when we plug that in there, we get 0 equals 2,500a plus 50b plus c. And the last one is 25 and 99.37. And when we plug that in there, this time we get 99.37 equals a times 25 squared plus b times 25 plus c. And when we do all of that and simplify that down, we get the following equation, which is 99.37 equals 625a plus 25b plus c. Okay, so there's our system in 3 variables. Now, what makes this really nice is we already know one of the variables. We know that c is 0, and that means we can just get rid of c in both cases. It doesn't matter because c is equal to 0. So what we really want to look at is this 2-variable system. 0 equals 2500a plus 50b. And 99.37 equals 625a plus 25b. Now I'm going to use elimination, and I am going to multiply this second equation by -2 to cancel out the b's. So that doesn't change my top equation, 2500a plus 50b. But now down here, I get -198.74 equals -1250a minus 50b. Perfect. When we add these together, the b's will cancel out. We get -198.74 equals 1250a, and when we divide by 1250 on both sides, we get the a is about -0.159. Okay, and once we have that, now we're going to take this value for a and plug it back into one of our equations, and when we do that, we figure out that b is equal to 7.95. So again, you're just going to plug in for a and then use that equation to solve for b, and that's what you get. So here's what we know now. We have 3 values for a, b, and c. So when we write our equation, it's going to be y equals a -0.159 x squared plus bx, which is 7.95x, plus c, which is 0. So that is our equation.